So, in yesterday's class, we saw a problem on solving symmetrical fault calculation using Thevenin'S theorem. Now, we will be seeing another problem. So, kindly go through the video.
In this class, we work out one problem on symmetrical fault calculation using Thevenin'S theorem. For the network shown in figure, the first question is draw the reactance diagram of the network. Second question is calculate the terminal voltage. Third question is if fault occurs at bus 4, calculate the fault current. This is the given network. This network consists of one generator, two transformers, one transmission line and one load. Generator rating is 15 MVA, 8.5 kV, subtransient reactance is 0.2 per unit. Transformer 1, 3 single phase transformers. Each transformer rating is 6667 kVA. 3 into 6667 kVA, that is equal to 20 MVA. This side is delta connected, this side is star connected. This voltage is 10 kV, this side is 100 kV. Reactance of the transformer is 0.1 per unit. The transmission line impedance is 50 ohm. Transformer 2, 3 single phase transformer. 3 into 6667 kV, that is equal to 20 MVA. This side is star connected, this side is star connected. This is 100 kV, this is 10 kV. The load is 10 MVA, 0.8 power factor lagging, 12.5 kV. First step, I choose base MVA and base kV. Base MVA is equal to 10, base kV is equal to 12.5. Next, I have to calculate the high voltage kV base. Here this is star connected, this is star connected. In star connection, line voltage is equal to root 3 times phase voltage. Delta connection, line voltage is equal to phase voltage. Therefore, 10 into root 3, 17.32. 100 into root 3, 173.20. Now, high voltage kV base is equal to low voltage kV base, that is 12.5 into HT by LT. 100 into root 3 divided by 10 into root 3. That is equal to 125 kV. That is a transmission voltage kV base. Low voltage kV base is equal to 12.5. High voltage kV base is equal to 125. Step 2, I have to calculate the per unit reactance of the generator, transformers, transmission line based on this base MVA and base kV. So the transformer 2 reactance, per unit reactance is equal to actual reactance value, that's a given reactance value, into V1 by V2 the whole square into SB2 by SB1. 1 is a given value, 2 is a chosen value. Therefore, XT2 is equal to given reactance J.1 into V1. V1 is 17.32 divided by V2. V2 is 12.5. 12.5 the whole square into SB2. SB2 is 10. This value base MVA divided by given value 20. That is equal to J.096 per unit. Next, I have to calculate the base impedance of the transmission line. Voltage is 125. 125 square divided by base MVA. 125 square divided by 10. That is equal to 1562.5 ohms. Now I can calculate the per unit reactance of the transmission line. Actual value by base value. Actual is 50. Base is 1562.5. Per unit reactance of the transmission line is J.032. Next, I have to calculate the low voltage kV base of the transformer 1. Low voltage kV base is equal to high voltage kV base into LT by HT. High voltage kV base is 125 into, this is LT by HT. LT is delta connected, HT is star connected, therefore 100 into root 3. Low voltage kV base is equal to 7.217 kV. This side is 7.217 kV, this side is 125 kV, this is 12.5 kV. Next I can calculate the per unit reactance of the transformer 1. Given value is J.1 into V1 by V2 the whole square. V1 is 10, V2 is 7.217 the whole square into SB2 is 10, SB1 that is 20, that is equal to J.096. The last is a generator. Given value is J.2, V1 by V2 the whole square, 8.5 by 7.217 the whole square into SB2 is 10, SB1 is 15, that is equal to J.185. Now I can easily draw the reactance diagram, that is step 3. All the values are in per unit. The generator reactance is J.185, transformer 1 reactance is J.096, transmission line reactance is J.032, transformer 2 reactance is J.096. The second question is calculate the terminal voltage. That is the voltage appear across these two terminals. Load power factor is given 0.8 lagging. Cos inverse of 0.8 is equal to 36.87 degrees. Per unit power is equal to actual power 10 lagging minus 36.87 degrees divided by base MVA, that is 10, that is equal to 1 angle minus 36.87 degrees. Voltage per unit is equal to actual is 12.5, base is 12.5, therefore voltage per unit is equal to 1. Current per unit is equal to per unit volt power divided by per unit voltage. 1 angle minus 36.87 divided by 1, that is equal to 1 angle minus 36.87, that is the per unit current. Now I have to calculate the voltage drop. I know the I have to calculate the value of X. X is equal to J.096 plus J.032 plus J.096. X is equal to J.224 angle 90 degrees. I is equal to 1 angle minus 36.87 degrees. I into X, voltage drop is equal to 0.224 angle 53.13 degrees. This is in polar form. In rectangular form, 0.134 plus J.179. Terminal voltage Vt is equal to per unit voltage, that is 1 plus drop, 1 plus 0.134 plus J.179. Terminal voltage is equal to 1.134 plus J.179 per unit in rectangular form. In polar form, Vt is equal to 1.15 angle 8.97 degrees in per unit. Now I can calculate the actual terminal voltage. Actual terminal voltage is equal to per unit voltage into base value. Per unit voltage is 1.15 into 7 point, base is 7.217, that is equal to 8.3 angle 8.97 degrees in kV. Actual terminal voltage is 8.3 kV, angle is 8.97 degrees. The third question is, if a fault occurs at bus 4, calculate the fault current. The terminal voltage is 1.15 angle 8.97 degrees. The Thevenin'S voltage is 1 because the load voltage is 1 per unit. Thevenin'S voltage is 1 per unit. Second step, we have to calculate the X Thevenin'S. Here the 4 reactances are connected in series. J.185 plus J.096 plus J.032 plus J.096, that is equal to J.409. Here the load impedance is equal to V by I. V is equal to 1, I is equal to 1 angle 36.87 degrees. Z per unit is equal to 1 angle 36.87 degrees, that is equal to 0.8 plus J.6. So this is 0.8 ohms plus J.6. Again these two are connected in parallel. X Thevenin'S is equal to J.49 into 0.8 plus J.6 divided by J.49 plus 0.8 plus J.6. So X Thevenin'S is equal to 0.08 plus J.307. Now I can easily calculate the fault current. Fault current is equal to E Thevenin's by X Thevenin's. E Thevenin's is equal to 1, X Thevenin's is equal to 0.08 plus J 0.307. So fault current is equal to 0.795 minus J 3.05 per unit. This is in rectangular form. In polar form, fault current is equal to 3.15 angle 75.39 degrees. So per unit fault current is 3.15 angle 75.39 degrees. This way we have to work out this problem. Thanks for listening.
So, in this class, we saw about a problem on symmetrical fault calculation based on Thevenin's theorem. Note that the problem we saw in yesterday's video and today's video are so much important. In the next video, we will be seeing about the Z bus impedance matrix building algorithm. So, thank you so much.